Welcome back, students. In this video today, we're going to learn about the conservation of momentum. In the past unit on energy, you probably remember the law of the conservation of energy, and that says that energy cannot be created or destroyed. It can only be transformed between different types of energy. This is somewhat similar to that law, but this is more specific to things that are in motion. In the case when some object has some motion, it will have momentum, right? It's a mass with velocity, so it has momentum. And then if that object collides with another object, after the collision, the momentum of the initial object and the object that it collided with, both those momentums will add together, and then that momentum will be conserved after the collision as well. So both those objects will still have momentum after the collision, but it might just be distributed differently between those two objects. But the total momentum is still the same before and after. Okay, if I put that in equation form, it looks like this. Okay, so here I have P1 initial plus P2 initial, or initial momentum of the first two objects added together is equal to the final momentum of each of those objects added together as well. And if I write this out more explicitly, it looks like this. Okay, so here in this equation, I just wrote out the same thing, but instead of writing P, I wrote mv for momentum. And then for the initial side, I have the initial velocity for the first object times the mass, and then the second mass times its initial velocity, which is going to be equal to the same thing on the other side, but just for the final state. So the final velocities instead of initial. Okay, next I want to go through a few conceptual examples where I can explain the conservation of momentum in real situations. Okay, the first situation I want to talk about is, let's say there's a skateboarder who is jumping on a skateboard that is stationary. So he's getting a running start and he's jumping on that skateboard. Okay, so initially he has some mass and velocity, of course. So we know he has, we'll say object 1 is the person, and he of course has velocity. So we have this term. And then since the skateboard is stationary, it has 0 velocity. So this term is 0. Okay, then after the skateboarder jumps on his skateboard, both him and the skateboard are going to have motion at that time, and they're both going to have the same velocity. So I can just use 1v. Okay, so I just have mass 1, that's the skateboarder and his velocity, final velocity, plus the mass of the skateboard and the same velocity, final. So this is how I would write the conservation of momentum out for that situation. Here I can see that the total momentum from the system is all going to be coming from the skateboarder who's getting a running start. And then after he jumps on the skateboard, that's considered a collision of sorts. He transfers some of that momentum into the skateboard, but of course carrying it with himself. In the case whenever someone is shooting a gun, we can say that the collision happens whenever the trigger is pulled and that bullet shoots out of the gun. It shoots forward with some momentum, and as a result of it shooting forward, it applies a force back on the shooter. So it's an equal opposite force, and that shooter is going to feel the same momentum going backwards. Okay, of course he has a much larger mass than the bullet, so his velocity is going to be less. But the bullet and the person have the same momentum. If momentum is conserved, we know that the momentum before is going to be the same as it is after the collision. Okay, before, if this is a shooter staying still with a gun, he has 0 total momentum, right? Because he's not moving. So that means that the momentum after has to also add up to 0. Yeah, so the momentum before is going to equal the momentum after. If there was no motion before, then that means that the momentum is going to be 0 before. It's going to be 0 after the collision. And the way that makes sense is that the momentum of the person and the bullet are going opposite directions, so they cancel each other out. Okay, so I'd write 0 for both the bullet and the person. They both don't have any motion before the trigger is pulled. Okay, then after the collision, the bullet will have some momentum, and so will the person, but it's going to be going the opposite direction. So technically, one of these velocities will technically be negative, so they'll actually just cancel each other out. Okay, but this is what that equation would look like for that situation. Okay, here I've drawn an example where I have a collision happening. Here's the before state, the initial state. I have one box of 5 kilograms, has an initial velocity of 2 meters per second, and then it collides with this stationary box of 2 kilograms, and because it's stationary, it has no velocity. And then after the collision, I know that this first box slows down to 0.5 meters per second, and I want to know how fast is this second box going if I know that momentum is conserved. Okay, if I can figure that out, I'm going to write out the conservation of momentum equation right here. Okay, I wrote my equation out here. Okay, so now I'm just going to plug in numbers here for everything I have. I have the mass and the velocity for everything in the initial state, so I can fill out this whole side. And then for the right side, the only thing I'm missing is the final velocity for the second object, so v2f. Okay, so I'm going to write everything out now. I plugged in numbers for all my terms now. I'm just going to go ahead and crunch the numbers. Okay, I know 5 times 2 is 10, and I know 2 times 0 is going to cancel out. 5 times 0.5 is 2.5, and then 2 times v2, that's my unknown. Okay, so now I can subtract this 2.5 to both sides, and I know 10 minus 2.5 is going to be 7.5. Alright, and then the last step is to get rid of this 2 that's being multiplied to the velocity. So I'm going to divide both sides by 2. Okay, and then this 2 will cancel with this one, and I'll have my velocity is equal to 7.5 divided by 2, which is 3.75. Okay, so I was able to calculate the final velocity of that second object, knowing the mass and velocity of the objects before the collision, and then just one of the objects after the collision. I can find the second object's velocity. Okay, hope this video helps you guys figure out the Google form, and we'll learn more about elastic and inelastic collisions this week. Thank you guys, see you next time.